All right, so we've seen how PCA can help simplify data by finding the most important directions of variance, but what if your goal isn't just simplification? What if you need to separate distinct groups within your data, like identifying different species of flowers, categorizing customer types, or diagnosing medical conditions? That's where linear discriminant analysis, or LDA, comes in. Imagine you're a coach trying to organize players into two teams for a big game. The players are scattered all over the field, and they're not wearing uniforms to indicate which team they belong to. It's chaos. Your job is to figure out a way to draw a clear dividing line between the two groups so that everyone knows where they stand. That's essentially what LDA does, but instead of teams, it's working with data points, and instead of a field, it's operating in a high-dimensional space. The first step in LDA is understanding class separability. It asks, what makes one group different from another? Let's say you're working with a data set of customers, where one group represents frequent buyers and the other represents one-time visitors. LDA tries to maximize the distance between the means of these two groups while minimizing the variance within each group. In simpler terms, it's making the groups as distinct as possible while ensuring each group remains tightly packed. Next, LDA constructs two key tools: the within-class scatter matrix, SW, and the between-class scatter matrix, SB. Think of these matrices as maps. The within-class matrix shows how much the data spreads within a single group. Are the points tightly clustered, or are they scattered all over? The between-class matrix, on the other hand, measures the distance between the group centers. Together, these matrices tell LDA how well separated the classes are and help it figure out the best way to divide them. But here's the tricky part. LDA doesn't just guess where to draw the line. It solves a generalized eigenvalue problem to identify the optimal directions, called linear discriminants, that best separate the classes. These discriminants are like pathways through the data, directions that maximize class separability. The eigenvalues tell us how much information each discriminant captures, helping us decide how many dimensions to keep. Once that's done, LDA moves on to selecting the optimal number of components. Typically, it reduces the data to one fewer dimension than the number of classes. So if you're working with 3 categories, you'll end up with 2 dimensions. This ensures you're preserving the essential information needed to distinguish between the groups without keeping unnecessary noise. Finally, we get to the big moment: transforming to a new space. LDA projects the original data onto the reduced dimensional space defined by the linear discriminants. The result? A clean, clear separation between classes that makes visualization and classification much easier. It's like taking a blurry picture and sharpening it until the edges are crystal clear. Here's why LDA is so powerful. It doesn't just simplify data, it simplifies classification. It's widely used in applications like face recognition, medical diagnosis, and even marketing. For instance, in bioinformatics, LDA can help identify biomarkers that distinguish between healthy and diseased patients. In marketing, it can segment customers based on purchasing behavior, allowing businesses to create targeted campaigns. But there's a catch. LDA works best when the data satisfies certain assumptions, like having normally distributed features with equal covariance matrices for each class. If those assumptions are violated, the results can be less reliable. And LDA is also sensitive to outliers. Just 1 or 2 bad data points can throw off the analysis. So what's the takeaway? LDA is your go-to tool when you need to classify data into well-defined categories. But it's not the only tool in your arsenal. What if your data doesn't have clear categories? What if you're dealing with a massive dataset and you need to uncover hidden patterns? For that, we'll need something a little more exploratory. Get ready, because next we're diving into the world of TSNE.